Hello, and welcome back to our discussions on technologies of herbal concentration and extraction. Today, we're going to be moving beyond just the science of botany and plant matter chemistry and start thinking about the engineering and systems perspectives. In this module, we're going to be asking the questions of how do we move the molecules from inside a plant into an extract, and then how can we maximize the extractions that we want? Today, we're going to be focusing on that first question. Our key concepts are going to be performances of material balances, understanding equilibrium in material balances, loss, yield, and recovery, mass transfer and diffusion, effects of grinding, and the roles of surface area and solvents in solvent-to-solid ratios. So we're going to really ask the questions of where do things go and how can we control that? Let's imagine that we have a peppermint leaf that contains 100 milligrams of menthol. After our extraction, we end up with 65 grams of menthol in our oil. Where do the other 35 milligrams go? They had to go somewhere. Well, in engineering systems, we really need to think about that in terms of accounting. We need to be able to understand where these 100 milligrams, which we started out with, end up. Through our extraction process, we have this menthol, we can put it into this extractive black box, and we end up with our essential oils. But some of that menthol is lost, and some remains in those soggy leaves, right? And so we're going to start thinking about our processes, need to think about our processes in accounting for where all of that material goes. Because no matter what we do, no process is 100% effective. And when I mean 100% effective, I mean if we start with 100 milligrams of menthol, we will not end up with 100 milligrams of menthol in our collected product. This brings us to the concept of a material balance, right? So in terms of accounting, where the material has gone. For the purposes of this class, which we're going to exclude nuclear reactions, we're going to say that matter cannot be created or destroyed, only moved around. This is going to lead to the overall equation or thought process of chemical engineering and sort of how we'll think about things. So the amount of a material that's going to accumulate in a system, right? And we can consider this black box, literally the black box, to be our system, is going to be how much of that material has gone in, right? So input, how much of the material comes out of the black box, the output, plus what is generated, right? So if we're counting on B, that's how much of A turns to B. So how much B is generated in this process minus how much is consumed. So if we're looking at B, that's how much of A gets transformed to B. And so this is going to be our overall equation that's going to help us figure out where all the material has gone and help us do our material accounting. So if we think about our molecular fate of this peppermint, right, it's going to be the input to our system. We're going to have generation and or consumption in here, so we can think about this in terms of, degradation of a desirable compound or generation of a desirable compound. And then we have sort of three outputs that we will be dealing with. One being, how much we're recovered in our final product, how much is lost, usually in terms of volatilization, so turning into a gas and being lost to the atmosphere, and then how much of our interested materials remain within that plant matter. So how much remain? And this is going to be just like we showed a few lectures ago, where we asked what happened to materials, and we said that we can, have the molecules be retained in the solids, lost to the gas phase, um, extracted, which is what we want, or somehow altered. And now we're just going to start putting some numerics to this, right? So we have this equation. Accumulation is input minus output plus generation minus consumption. Here, any arrow that's pointing into our black box is going to be our input. Any arrow that's coming out of the black box is going to be some sort of output. And then if we have a reaction inside that black box, that's going to be either the generation, if it's turning into it, or the consumption if it's being transformed. Okay, so we'll think about things again in terms of a few definitions. So once again, remember back a few lectures, we have mass fraction x of A, which is the mass of A over the total mass. We have yield, which we will be defining as the mass of oil in our final product divided by the mass of oil in the incoming plant. And then selectivity, how much of the target oil is in the final product over how much mass is in that is the final product. And then quality is less numeric. It's how refined is this. So let's go back to our example. Let's take and assume that we have a bunch of leaves, peppermint leaves, and that we have 100 milligrams of menthol. And that's what's in here originally. 65 milligrams of those are recovered in our oil. Some testing of what remains in the leaves after the recovery process found there were 15 milligrams left in the leaves. So my question is to you, how much menthol was lost and what is our yield? We are going to do this in a few different steps. First, we're going to set up our mass balance. That's our overarching equation. And we have accumulation in the system is equal to input minus output plus generation minus consumption. So we can look at this extractive process and we can say that we have stuff coming in, stuff going out. We are going to assume that nothing is accumulating in the system. I've put whatever the peppermint is into my extractive device, and at the end, I've cleaned the device. There's nothing left in the device. I've put 100 milligrams of menthol into my extraction system, so my input is 100 milligrams. I have different sets of outputs. There's nothing in this system that says we're going to generate more menthol, so that's going to go away and go to zero. And but there, we could still have some sort of consumption degradation. So we're going to leave this here for right now. So let's look at these remaining terms that we don't know. We don't know output or consumption because this is going to be zero, and this is going to be zero. So if we look at our output, we have the 65 milligrams that were recovered, the 15 milligrams that were left in the leaves, and any amount of vapor which is lost. Okay, we can just say that this is X milligrams, right? Because we don't know. So if I put these into numbers, we have zero accumulation, 100 milligrams in. We subtract off the output, so that's 65 milligrams plus the 15 milligrams in the leaves, plus some amount that's lost to vapor. And then we also subtract off the consumption. If for our intents and purposes, we don't really care when answering this question or, trying to figure out how much menthol we've lost, whether that menthol was lost due to vaporization or some sort of degradative mechanism. So I'm going to combine this terms of the x milligrams of vapor loss and some x milligrams of consumption. So our final equation says 0 equals 100 milligrams in minus 80 grams accounted for minus x milligrams that are lost or consumed. Right? So if I do this solve for how many milligrams were lost or consumed, I end up with 20 milligrams unaccounted for. Okay, so let's think about this question, how much is lost? Well, 15 milligrams are in the leaves, which might be recoverable, but maybe not. And 20 milligrams were irrecoverably lost, right? So those are either lost to vapor or some sort of reaction. We're not getting that back. So in total, we've lost 35 milligrams. Even though we have 15 in this in those leaves still, we weren't able to extract it. So those are lost. This gives us a yield of 65 milligrams over the 100 milligrams. So our yield fraction is 0.65 or 65%. Okay, so now we've walked through how we can do mass balance to think about, you know, how we can not only get information about how much is recovered, but we can start looking at how much we're losing to vaporization, and then what's maybe remaining in our leaves, and how these are going to contribute to our effective yield. All right, so if you remember yesterday or last time, we had said that, when I'm doing liquid-liquid extraction, I have some amount of material that's left in the water. Well, we could do the same thing here, right? I could take these leaves which exist and do a secondary extraction process to try to recover some of those 15 milligrams. We can do this sort of mathematically or engineering wise by having some two units. We could have one unit of extraction where I pull off the oil, and then I could have a second unit where I add maybe some new solvent or something else to pull off more of that more of that menthol. Right? And so we can draw this as a sort of diagram showing multiple units where I have, maybe the menthol or the mint leaves going in plus some water. I get my first product coming out. So that might be the that might be our first oil. Then I lose some vapor, but then I have the material goes into the second unit where I maybe add more steam, more water in order to have this run. And then I end up with my final product. So when I have multiple units, we can do these mass balances around multiple places, right? And we can break down each of these intersections and units, unit operations, we'll call them, and we can use the method that I showed before with a single unit, right? So I can do this over this entire place where I look at how much mint is going in and how much oil is coming out. Maybe oil and leaves. I can do this at each intersection. I can look at um, an individual unit operation. I can look at splits in lines, and I can look at the overall unit too. For more details, I'm going to put a link to a fuller video that just focuses on mass balances if you are curious, from one of my other classes. But I just want you to get this idea of we can represent these processes in these sort of black box fashions, and we can do this accounting or mass balances to see where our different products are going to go. One of the key things that I want you to realize is every single unit operation that I do, right, so each of those black boxes is going to include some sort of loss. So let's take again our mint. Even just handling the mint is going to have some sort of loss, right? As I'm moving that mint, it's volatilizing some of those trichomes just through evaporation. If I then grind the mint, I'm probably not getting every single little fleck of this mint that comes out of the grinder into my extractive process. And I'm going to have more vaporization. When I go to do the extraction, let's say I'm doing liquid solid extraction, so I've got a solvent extraction. I'm going to have losses because there's material still left in the plant. And I have volatilization. Once I take this to filter it through, not all of the material is going to be filtered, right? Some may still remain in the plant matter, right? And then finally, once I've bottled it, that bottle hopefully minimizes evaporation, but we can still have decomposition, right? And so as we're thinking about these systems, we want to find ways to minimize losses at these steps to try to enhance and maximize how much of our extract we get. Okay, so now that we've talked about these different losses, we can think about this in terms of these black body process flow diagrams, or so this is what this is called, a sort of block diagram, process flow diagram that is going to represent these steps. So we can take grinding, consider that a unit operation. Extraction is one unit operation. Filtering is a unit operation, right? So I take the plant material, that's our mass in. If I think about what's coming out, right, we have the ground mass that's going to go to extraction. I have any vapor that I'm losing, and I have any solids which get caught or left in that grinder. If I'm doing a liquid extraction, the second unit operation, I have the solids coming in, some sort of solvent coming in. I have any vapor which is lost, and then I have the solid remnants of the leaves and the liquid, which will move to our secondary extraction step. Here I'm doing this separation via a filter. Again, we have a vapor loss, and we have any solid waste which is caught in this filter, and our final product, which is what we want. Okay, so we've got this, we can represent these processes that we're doing: grinding, extraction, separation of the liquids and solids, and we can draw out this diagram. We can look and determine what these, how much is leaving as vapor, solids, liquids, etc., using concepts such as equilibrium, right? So we spent a long time last time talking about equilibrium. We can use that information in these diagrams to determine how much is leaving as a vapor versus in the liquid phase, or how much is remaining in the solid versus the liquid phase, right? So those K partitions that we talked about last time can be used to determine how much is, what fractions are leaving in these different phases. Again, um, you know, there's a link to a fuller discussion of how we can incorporate this in mass balances in the uh, show notes. Okay, so now that we have a basic understanding of how we can do the accounting and plot out our process, I want to bring up to the point, even though I just said we can use equilibrium, that none of these processes are instantaneous, right? So um, even if we want the molecules to come out of the plant and they want to leave the plant, no, they don't come out immediately. Now, to give you an example, let's imagine that you're in a locker room and somebody sprays Axe. How long is it going to take until you smell it? Well, depending on where you are in that locker room relative to the person who's spraying the Axe, it's going to take a different amount of time, right? So let's say at time zero, somebody puts on way too much Axe. Locally at that person, which is standing maybe here, the concentration or how much X is around is very, very high. And the farther you are away, right, there's all these happy people in the locker room, they don't smell the X because it's that concentration shown in this red line is too low for them to notice. But after maybe 1 second, that this spray has started drifting to the right, and the concentration of X has increased as we move farther away. So that first person who's closest to the guy who's sprayed X now is feeling a little bit sick because, of course, they sprayed way too much, right? And then over time, this concentration is going to move to the right. That second person, the next person over is going to smell it. And then the next person over will smell it a little bit later until finally everybody can smell that X. Right? And so what you can see is, there's some sort of time associated with the movement of these um, stink particles or fragrance particles from the beginning out to the end, right? And so we can sort of reference this, and as the particles move out, their concentration starts decreasing and evening out over space. And this process is called diffusion. So it's the movement of molecules from high concentrations to low concentrations. Right? And so this is what we want to do in plants, right? We want to move the molecules from our high concentration in the plant to wherever we want them. Okay? So we can think about this not necessarily just with X, but we can think about this in terms of our plant molecules. Let's take an example of linoleal acetate moving from our leaf, our lavender leaf into solution. Right? Initially, we have these lineal acetate molecules sitting within the leaf. There's they're in the cells. There's the germinal cells which are protecting the leaf. We put in water, and then we have this high concentration of our nice smelling molecules that, and the low concentration out here. They want to move out. Right? And so first, the molecules near the surface are going to start diffusing outwards over time. The distribution within this plant leaf decreases, and the concentration within the solution increases. What the difference in concentration between the leaf and the solution is becoming lower. Um, and as time goes on, more move out, the concentrations start equilibrating until at the end, we've reached equilibrium, and the number of molecules moving out of the leaf into solution is happening at the same rate as molecules moving from solution back into the leaf, right? So this is our equilibrium state. We can numerically put we can put numerics to this process of diffusion. And diffusion is most generally covered and mathematically described using what's called Fick's law. I'm not going to get into don't want to get into the details. I'll again post another link to an entire series of videos talking about diffusion if you're interested. But what I want you to know are sort of the three, or sort of the three things that are going to control diffusion, right? So here we have flux J of molecule A. So this is how much stuff is moving through space per time. And that is equal to our diffusion constant. So this is a constant that says how fast the molecules are capable of moving. And this is controlled by temperature. And that is multiplied by this ratio of the concentration difference. So how big is the difference in the concentration of the molecules at one location versus another, and how far that molecules need to move, right? So what's this distance over which this concentration distance difference has been measured? And this, for the engineers and the people who have taken more advanced math, right, is our concentration gradient. Okay, so I'm not expecting you to solve these equations, but I do want you to know, right, if I want to increase how much stuff is moving, I need to either increase um, the how fast things can move, right? So I can do that via temperature. I need to increase the concentration gradient. Um, so I need to have something that's going to remove the molecules once they're out of the leaf, or I need to have shorter distances over which those molecules need to move. Okay? So these are our key concepts. All right, and so how these are going to be applied, right, of how well things can move are going to be dictated by our oil-containing structures. So remember, we have sort of three major oil-containing structures, trichomes, oil cavities, and resin ducts. And importantly, where they live or they reside, those trichomes are going to reside outside of the tissue, plant tissue, while the oil cavities and resin ducts are going to live inside the plant matter, right? And so when I think about this, if I have our oil reservoirs and similar things to oil ducts, right? I need to get these molecules that I'm interested in, maybe say these orange pigments in these cells, which reside in sort of this leaf. So here's the leaf. If I turn it on its side, I have the top of the leaf, this sort of side purview. I need the molecules that are sitting within those oil cavities to fuse out of the system. Of course, this is going to happen slowly, naturally, because these oil cavities are designed to retain the oil, and the surface of the leaf is designed to keep things in. So we generally have to rupture the oil cavities and break those dermal cells, epidermal cells that sit on the structure of the leaf. But once we've done that, we're now able to have diffusion of these oil molecules out. And what that looks like is here I have a diagram where this vertical line indicates the distance from the center of the leaf. This line indicates how much, what the oil concentration is. We end up having these curved gradients. So the farther away I get, the lower the concentration, and it sort of asymptotically reaches zero. Okay. If I have an external structure, right, so our trichomes, we can directly start having diffusion once I'm exposing it to either temperature or concentration gradients, because we don't need to rupture those cells or disturb the leaf's surface. But we're still going to end up with this drop off in concentration as I move away from the leaf surface. All right. So there are, in addition to heating things up, there's some effects that we can rely on to try to get things to move faster. And I want to talk about this, and think about this in terms of surface area effects. So let's think about our oil cavities again. There are two major concepts that are going to dictate um, the system. So one is the volume, so how much stuff is there. And in our analogy, we can think of it as what is the size of a room or a box containing these scent molecules. And the surface area, and we can think about that as the door, right? That's the area through which these molecules must move to get out of the leaf or the box, right? And so if I think about this, if I have the same number of molecules and I have a room or a bunch of people, and I have a room that's 100 cubic meters and a door that's 10 cubic meters versus the same room, 100 cubic meters, but the door is 20 cubic meters, right? Which one can the molecules leave faster from? Well, obviously, I think, if they're trying to leave here, everybody's going to have to line up and go through one by one, versus through this door, we can get maybe 3 or 4 of these molecules all moving out at the same time. Okay, so this is, we can generalize this instead of having specifics of saying, our volume is 100 cubic meters and our door is 10 cubic meters. We want to generalize this to any sizes, and we do this by having a surface area to volume ratio. So what's the area through which things can leave divided by how much stuff there is to leave, right? And so if I look at this room on the right, it has a surface area to volume ratio of 10 versus, I'm sorry, this should be backward. This is backwards. It has a surface area to volume ratio of 0.1, and on the right, it has a surface area to volume ratio of 0.5. So significantly larger. We're going to expect to see, sorry, 0.2. The side is 0.2. We expect to see significantly larger diffusion out of this system. Okay. All right. So a lot of times we want to maximize that surface area to volume ratio so that we can get stuff out. And we do this generally by grinding. We can take our plant matter, I put it in some sort of grinder, I chop it up into tiny little bits. I now have a bunch of small particles instead of a few very large leaves, right? So when I put this plant in this extracting solution, I have a much larger, over here in the ground plant, I have a much larger surface area to volume ratio compared to this leaf. Additionally, not only do I have more area through which to move, but if I only have a single leaf sitting at the bottom of this jar, I have a really large distance over which these molecules need to go, where they're the farthest from the leaf as possible. So I end up having large dx's in terms of flux, versus when I have ground materials, the distance that these molecules need to go to be as far away as possible as any other molecules are much smaller. So I have a smaller dx, larger flux. Okay, so grinding is really useful. I increase my surface area to volume ratio. I increase my flux by increasing the gradient, and I end up breaking down these structures that facilitate the diffusion out of the leaf. Okay, so once again, this doesn't happen all at once, right? If I take those ground particles, I put it in solution, it's going to take some sort of time for the menthol to accumulate in the solution. We can generally plot this as the extraction yield on the y-axis over time, as the, and I can take measurements of the solution and I can see how much I've pulled out over time. Initially, we have what's called the washing stage. So this is a rapid removal of molecules which are maybe sitting on the surface. And then I'm left with the diffusion stage, where that those materials must diffuse out. So why is this diffusion stage, sort of slow, and then it gets slower with time? It's going to asymptotically reach equilibrium. And this is because the concentration in solution increases, and the amount of and the concentration in the plant decreases. So if I look at my flux out of the plant, my gradient, right? So this change in concentration within versus without is shrinking. Okay, lower concentration difference, lower flux, slower extraction. All right, now let's do a quick thought ratio. We've said we really like to chop up these plants, but there's more to that. We also need to think about our solvent to solid ratio. So here I'm showing again some leaves. This time let's assume that this is lavender. Here we've got our linoleal acetate in solvent, and I can mix my solvent to plant matter in, say, a 1-to-1 ratio. So as much solvent as there is plant matter, a medium solvent ratio, so 5-to-1, or a high solvent to lavender ratio. If I look across these, this high solvent ratio is really going to drive extraction, right? I've maximized my concentration gradient. I'm going to get as much as I possibly can, right? On the other hand, this 1-to-1 ratio, I'm going to minimize, I have a really minimal amount of concentration gradient. I can't push it that hard. It's going to take a long time to get those molecules out. And even then, right, if I think about partitioning, right, I should get way more molecules out here than here. When we have a medium solvent ratio, we can get all of our plant matter solids submerged. I can have a pretty good concentration gradient to drive the molecules out, and there's enough solvent there so that I have, at equilibrium, I get most of those molecules out. But if I look across these three sets, we have a problem in this high solvent ratio. One being the final concentration of our valuable molecules is relatively low. People want concentrated smell, right? We're here to concentrate these molecules in an easily usable form. Additionally, I have spent more money on my solvent. If I have to do any shipping, I have to do any bottling, right? There's additional cost with just having more volume to handle. So if I look at this in terms of recovery, the 20-to-1 solvent to plant matter ratio gets, hypothetically 92% recovery, so the highest of all three, but it also is going to have the highest cost, right? So I have this balance that I have to take into account. Maybe think about this in terms of making tea. If I put a tea bag in a glass with very little water, I get a really concentrated solution, but I maybe don't get everything that I could. Versus if I throw a tea bag into a bathtub, I'm going to get, more of that the caffeine, the flavor molecules out of that tea bag, but the water is going to taste very weak, right? So we have to have this um, uh, balance between getting everything out and having a good quality product. Okay, so what I want to think about again, now that we've talked about some of these engineering problems, are go back to this graph. We have our three major storage structures: trichomes, oil cavities, and resin ducts. And now we can start putting, instead of just saying that, these trichomes um, simplify extraction, we can start seeing why, right? Because they're sitting on the surface. Um, the diffusion lengths over which they must move are significantly smaller than the oil cavities and the resin ducts. If I look at the oil cavities and the resin ducts, here the oil cavities tend to sit near the leaves while the resin ducts sit farther in, right? So these resin ducts have to move greater distances, right? Greater distances, longer times, or a higher heat, right? So all of these pieces are coming in to help us think about how we um, are going to engineer this system. And of course, there are engineering trade-offs with this, right? So in um, how we want to deal with maximizing this extraction, right? So in order to deal with the longer diffusion lengths or slower diffusion lengths of, say, those resin ducts, we could say, okay, I'm going to use smaller particles. And that's going to give us faster extraction and greater recovery for however long I want to extract. But with smaller particles, it can be hard to remove the solids at the end. I'm going to have more fines, right? So the very, very small particles, which are going to maybe end up in my final product. Um, because I've enhanced the diffusion, not just of the molecules I want, but of everything, right? So I can end up with more undesirable products in my in my product. We could increase the temperature, right? I'm going to increase the diffusion constant, faster recovery, greater recovery, but I'm also increasing the rate of my degradation and increasing the rate of diffusion of undesired compounds. And lastly, like we spent a fair amount of time talking about, I could increase the amount of solvent. Again, faster recovery, more recovery, faster recovery, but in, uh, I now have higher expenses. I have more extraction of other things, and I need to handle just more liquid. All right, with that, I'm going to leave you with this question of we've spent a lot of time talking about menthol, how would you think about increasing menthol extraction? At the end of today, hopefully you now have an idea about doing materials balances, thinking about equilibrium and materials balances and where that fits in, uh, thinking about loss and yield. We spent a fair amount of time talking about mass transfer and diffusion, and then the effects of various processes like grinding on and solvent areas on mass transfer and diffusion. Next time, we're going to delve a little bit more details into the engineering of these various systems. All right, have a great day.